Okay. Okay. So yeah, I've just started the recording. So first I'll give a quick introduction to today's speaker. Then we'll have about 45-50 minutes of presentation, and then I'll leave about 5 to 10 minutes for questions at the end. Please ask questions during the talk. It makes it a little bit more interactive. If you have any problems, just send me a chat, and please keep on mute when not asking questions. It just makes things a bit simpler. So today I am very pleased to introduce Shlomi Reuveni from Tel Aviv University. Shlomi completed his PhD in 2014 at Tel Aviv University on tandem stochastic systems, the asymmetric simple inclusion process. He then had a postdoc at the Department of Systems Biology in Harvard Medical School from 2014 to 2017. Then returned to Tel Aviv as a senior lecturer or assistant professor at the School of Chemistry. Research interests are statistical physics, physical chemistry, biological physics, stochastic processes, and operations research. Today, Shlomi will talk about the inspection paradox approach to stochastic resetting. Thank you, and over to you, Shlomi.
Thank you very much. Can everybody hear me well?
I think we got some nods.
Was that a yes?
I think so, yeah.
Yes. Okay, perfect. Okay. Thank you very much, Peter, for this kind introduction. And thank you, Martin and Peter, for inviting me to speak in your Statistical Physics and Complexity webinar series. It's a great pleasure. You see somebody in the chat. Oh, yeah, okay. It was Martin just saying yes. Okay. So the title of my talk today is Inspection Paradox Approach to Stochastic Resetting. And perhaps the first thing I want to do is tell you what the inspection paradox is. So here on the left, you see William Feller, who popularized the inspection paradox with the bus stop example that he gave in his book, famous book on probability theory. And what he imagined is a passenger arriving at a bus stop at some random time. And he showed that this passenger could experience a waiting time that is on average longer than the average waiting time between bus arrivals. And so this looks a little bit weird, hence paradox. Because if you come sometime after a bus departed, sometimes was spent, and then you expect naturally to wait less. Nevertheless, there are situations, and I'll show you that they're actually prevalent, in which you could end up waiting more than you expect, and more than the average waiting time between bus arrivals. And then what I'll try and do, and this is the premise of my talk today, I'll try to connect this with the stochastic resetting, which is an emerging field in statistical physics. And in fact, I'll try and show you that much of what we know on stochastic resetting can be understood with elementary tools, really elementary mathematical tools, if one is only made aware of the inspection paradox and understands its ramifications on stochastic resetting. So this is the premise of today's talk. And before I start, I would like to give credit where credit is due. So this talk is based on a paper that we published, a viewpoint paper that we published, the inspection paradox in stochastic resetting. It was published in the Journal of Physics A as part of a special issue, Stochastic Resetting Theory and Applications, in celebration of the 10th anniversary of diffusion with stochastic resetting, which is a beautiful paper by Martin Evans and Satya Majumdar that I will refer to multiple times today. And I hope that by the end of the talk, you'll understand why are we celebrating the 10th anniversary of this paper. Who actually did the work? Two brilliant postdocs, Dr. Arnav Pal who now moved to the Institute of Mathematical Studies in Chennai to start his own group, and Dr. Sarah Kostinsky, who is now at the KITP, but will soon start her own group at NYU Physics. So these are the people behind the work. And here's a reference. And I think that now we're all good to go. And we can start by discussing the inspection paradox. So what is the inspection paradox? I want you to imagine a bus stop, and I wanted to imagine that it's perhaps Switzerland. So buses arrive at the station every 10 minutes, or more generally, there is some deterministic time that governs the inter-arrival time of buses, and they arrive at every time t. Let's call this this deterministic time that separates bus arrivals, capital T. So this is going to be the first example that we consider. And now a passenger arrives at the bus stop at some random time. And what I want to do is ask how much time will this passenger wait? So we'll call this time T-res for time residual, the residual waiting time of this passenger. And I'm interested in the average of this time, basically the average waiting time of a passenger until a bus comes and picks him up. So you can argue as follows: if you arrive at a random time, you're basically going to fall in one of these intervals, and they're all the same, and there's no bias, so you're equally likely to fall to the left or to the right of the midpoint of any interval. And so just by symmetry, you could argue that this mean residual waiting time is just half the size of this interval, and you'll be right. This is indeed the right answer. Now I want to consider what noise does to this question. So instead of deterministic bus arrivals, let's consider now bus arrivals that follow a Poisson process. So they arrive stochastically, and more specifically, the waiting times between bus arrivals are taken from an exponential distribution. This is the meaning of a Poisson process with some mean, which will denote like that, the average of capital T. And I want to ask the same question. You arrive at some random time. How much time are you going to wait? So you can argue like you argued before. You're going to land at some interval. There's symmetry. You're equally likely to land to the left or to the right of the midpoint of any interval. And because these intervals are this large on average, then the average waiting time that you'll end up spending, this guy, is just the average size of the interval, just half the average size of the inter-arrival time, average inter-arrival time. This, however, turns out to be the wrong answer. So it's not correct, and the right answer is that the mean waiting time is going to be equal to the mean time between bus arrivals, which is already a little bit weird. But you can understand this if you recall the memoryless property of the exponential distribution. So because bus arrivals, the times between bus arrivals are taken from an exponential distribution, and the exponential distribution is memoryless, if you come at some random time and you know that no bus arrived during this time period, then from this point going forward, the waiting time is exponentially distributed with the same mean. This is the memoryless property of the exponential distribution. And if you know about this, then you can understand this result. But if not, and even if you do, maybe you're already moving in your chairs. How is this possible? And things get even a little bit more complicated and tricky when you consider general bus arrivals, so waiting times that are not exponentially distributed but come from some general distribution. And then if there's any justice in the world, you would expect that this mean residual, this mean waiting time, the mean of the residual waiting time, is going to be somehow bounded between half the size of the interval to the total size of the interval. So perhaps you know the deterministic and the exponential or some extreme cases that we considered, but in fact, it's not true. This is also not true, and there could be situations, and I'll show you in a second such situations and explain how do they arise, where on average you're going to end up waiting more than the average size of an interval, the inter-arrival time interval. How is this possible, right? How can you come in between two bus arrivals and still end up waiting more? So the resolution to this paradox really comes by observing that you have a sampling bias here. So when you come at a random time point, what you do is you sample time points with equal probability. But this also means that you're biasing towards larger intervals because they have more time points in them. So let's see really how does this come about. If we'll consider the empirical mean of the residual waiting time, then if you tell me that you landed at some interval I, then really there is no bias. You're equally likely to land to the left or to the right of the midpoint of this interval. Hence, the mean residual waiting time is just going to be half the size of this interval. But in order to get the full mean, you need to multiply this by the probability that you really landed in this interval, and then sum over all the possible intervals. The probability to observe an interval ti, or to come at an interval ti, is proportional to its length, and then you need to divide by the total length of all the intervals. And so you see that what happens after a slight rearrangement is that you become sensitive to ti squared. And then here I also divided numerator and denominator by n. You'll see why in a minute. So here you have the empirical second moment, and here you have the empirical mean. And when you take the limit n goes to infinity, what will happen is that these things will converge to the second moment of the inter-arrival time distribution and the first moment of the inter-arrival time distribution. And this is going to be the, on average, how much you wait until a bus comes and picks you up. It's convenient to rearrange this formula and write it as follows: basically half the mean, then times 1 plus, and here I have the standard deviation of the inter-arrival time distribution over the mean. This thing is called the CV, or the coefficient of variation, which will play a big role in our talk today, and it is squared. So this is just a rearrangement of that. And why is it convenient to write it like this? Well, now you can see that if there are no fluctuations in the deterministic case, standard deviation is 1, and what you get is basically the deterministic result. The waiting time is half the size of an inter-arrival time, half the average inter-arrival time. If, however, inter-arrival times come from an exponential distribution, for the exponential distribution, the standard deviation is equal to the mean, and then CV is 1, the 1 and the 1 kill the 2, and the mean residual is equal to the mean. So the two cases that we already considered, they check out. But what could also happen is that you'll look at some inter-arrival time distribution with fluctuations that are larger than those that you have for the exponential distribution, a standard deviation that is larger than the mean. And for these kinds of distributions, what you will see is that you end up waiting a time that is longer than the mean inter-arrival time between buses. And so really this could happen, but it's not a paradox, rather a very counterintuitive result. And it comes about because you have an inherent sampling bias. If you come at a random time, you are biased to sample larger intervals, and these will bias your waiting time to be larger than what you expect it to be. And in particular, you become sensitive to fluctuations in the inter-arrival time of these buses. So this is all fine and nice, but aside from buses, where else does it apply in life? So it turns out that in many places, you see the inspection paradox. But for the purpose of my talk today, I want to talk about stochastic resetting, and in particular about what I call the resetting paradox. Okay, so I want to think about the effect that resetting has on the completion time of a process. And to be concrete, I'll consider a simple process. First, let's think about motion with constant velocity. So you have a particle, you have a target, the distance between them is L, and at time 0, the particle starts moving towards the target at a constant velocity V. And you ask how much time does it take the particle to reach the target? Just L over V units of time. Nothing stochastic here, completely deterministic, very simple. Now, what happens if you take this process and you stop it and start it anew from time to time? Then you could have situations like that. So I want to think about resetting with some constant rate R. And this basically means that for every infinitesimal time interval delta t, you flip a coin, and with probability delta t times R, you reset the position of the particle. So you could have things like that. The particle starts moving, then resetting happens at some time, take the particle, place it back at the origin, and then it goes again and again until the particle is eventually able to reach the target. So how much time will it take such a particle to reach the target with resetting? Obviously, now it's not deterministic. There's going to be some distribution of times, but without doing any fancy calculations, you'll agree with me that whatever the mean was before, now it has to be more than that, because the last trial, the successful trial in which the particle is able to reach the target, this took L over V units of time precisely. But previously, because the resetting rate is larger than 0, there could have been, with probability that is non-zero, some failed attempts, and these took time, and this time feeds into the mean. And so the mean with resetting is going to be larger than the mean without. Resetting hinders the completion of this process. And you can say, yeah, it's not surprising if you take a process and you interrupt its completion by stopping it and starting it anew from time to time. All you can achieve by doing that is basically hindering its completion. So perhaps here's another example, and this is the diffusion with stochastic resetting. Beautiful paper by Martin Evans and Satya Majumdar. And what they did in this work is they took something that every physicist knows about, diffusion, and they spiced it up a little bit by adding resetting to this process. So you think about a Brownian particle, it's diffusing, but then from time to time you take it back to its original position, and you do this with rate R. And so now you can ask the following question: when will the particle reach the origin or any other point? That doesn't matter. And you could argue maybe, previously it was free to roam around, right? But now resetting focuses the particle around its initial position. And so it's going to be hard for it to explore other places. And so maybe now what will happen is that, again, like in the previous example, the particle will take more time to reach the origin with resetting. So resetting will hinder process completion than without. But this turns out to be completely wrong, completely wrong. And I want to say a few words about this. So you basically have the same problem, same ingredients, a particle that starts somewhere in a distance L to the target, and then the particle, instead of doing ballistic motion, it's going to diffuse. So this is a classical problem, and we can ask how much time it takes the particle to reach the target. Classical results. This is the probability density that governs this first passage time. So there's a distribution, and this is the density of this distribution, and it's parameterized by the distance to the target and the diffusion coefficient. One thing that should be said about this distribution is that it's normalized to 1. And so this means that the particle will reach the target with probability 1 if you wait long enough. However, the tail of this distribution is heavy in the sense that it drops like 1 over t to the 3/2. And so if you multiply by t and integrate, what you'll discover is that the mean diverges, which is one of the surprises that you have when you first learn about first passage processes. So without resetting, this process will complete, but on average, it will take it an infinite amount of time. What Martin and Satya were able to show is that when you add resetting, things completely change. So this process will complete in a time that is finite, regardless of the resetting rate that you pick. So as long as you reset, the resetting rate is larger than 0, the mean first passage time of this particle to the target is going to become finite. So why is that? Well, for diffusion, we have a strong physical intuition why this happens. The particle diffuses and it can reach the target, but what could also happen is that it will diffuse and do some long excursion to the other side, basically go to the left. And this is really what's giving rise to the tail of this distribution. What resetting is doing is preventing these long excursions bringing back the particle to its starting position when it got lost. And so it cuts the fat tail of this first passage time distribution and regularizes it such that the mean and actually all moments converge. But then it's also natural to ask what happens in the general case. So you can think about other processes, not necessarily diffusion processes, with resetting, and think about how resetting affects the completion time of these processes. And all of this falls under the title of first passage under restart. So maybe you have a group of searchers, and these guys are looking for a target, but then bad weather or nightfall will force these guys to go back to base, and they'll have to start the search anew the night after, or the day after, sorry. Maybe you have a computer algorithm that is searching for a solution in a tree of possibilities stochastically, but then chance could send the algorithm down the wrong path. So perhaps you want to code restart into your algorithm so as to give it a second chance of finding the right solution to the problem. And in fact, computer scientists do this all the time when dealing with stochastic algorithms. Maybe you have a molecule, you prepare it at some excited state, but it decays to a low energy state that is not the product you were hoping to get. And then maybe by mechanical manipulation or a laser pulse, you can re-excite this molecule, and perhaps now it will decay to the right product. And in all these cases, we want to know what is the effect of resetting. In all these cases, we have resetting baked into the cake, and we want to know what is the effect of resetting. So the standard way to go about, and this is not the way that I'm going to do this today, is by following what we now refer to as the renewal framework, which applies to first passage problems, but also beyond. And I'll touch on that in the end of my talk. So what you imagine is that you have some starting point, some finish point, and there's a first passage process that takes you from start to finish with some random completion time. And on top of that, you add restart, and you want to ask how much time it takes you to complete the process in the presence of restart. So you have a completion time T in the absence of resetting, and some random resetting time R, and the completion time with resetting is given by what we refer to as a stochastic renewal equation. So on the left, you have the completion time with resetting. What does it equal to? Well, either way, you're going to have to wait a time that is the minimum between R and T, because it's either that the process is going to complete or you're going to have resetting, whatever happens first. If the process completes, it completes. If you have resetting, then, and this is an indicator function that is one only when resetting happened before completion, then you're going to have to start anew. And this guy right here is an independent and identically distributed copy of this guy. And once you have this equation, you basically can get anything you want. You can get the mean, the distribution of the completion time with resetting. And moreover, you can express these in terms of the underlying quantities, the completion time in the absence of resetting, which makes your work much easier, and this the distribution of this resetting time. I want to give an example before I go on. So if you take expectations on the previous formula, you'll discover that the mean first passage time under resetting is given by the average of the minimum between R and T, and then this is divided by the probability that T is smaller or equal to R. And if you specialize to the case of resetting at a constant rate, then you see that you can write this formula in a very convenient form. So you define the Laplace transform of the completion time distribution as the expectation of e to the minus RT, where T is the completion time without resetting. And this guy is now just 1 minus the Laplace transform over R, the resetting rate, times the Laplace transform. One thing that you can appreciate is that you can tell me what is the mean completion time with resetting just by looking at the process without resetting, which is a great advantage. And we really learned a lot from this. Not only the mean, you can also do that for the distribution and so on and so forth. Another thing that you can appreciate is that even in situations where the mean completion time without resetting diverges, this Laplace transform does not diverge. Sorry, is not zero. Why is this important? Because the only way in which this mean completion time with resetting, the only way in which it can diverge is either by r being 0. So if you reset at some positive rate, this is non-zero, or by this being 0. And this is not 0 if this is only 0 if t is infinity for all cases. Basically, when you have a process that never completes. If on average the mean diverges, but the completion time is finite, such as the integral. So in the case of diffusion, converges, and even if it doesn't, even if there is some probability to complete in finite time, this guy will not be 0. Hence, if you take a process that on average takes an infinite amount of time to complete, introducing resetting will always help it complete in finite time. So a lot we can learn from this, but one thing that we can't learn from it is, just staring at this formula, why does it work? So there are situations where you're going to encounter different processes that have finite moments. So completion time has a finite mean, variance, all the other moments also. You introduce resetting and the process ends faster. Why does this happen? So you can plug in all sorts of examples into this formula and play around, and we've learned a lot from it, but fundamentally, why does it happen? And this is what I want to answer in the second half of my talk. Why does resetting work? And the reason it works, maybe there's another. We don't see my mouse. Okay. I hope that you can see my cursor as I'm moving it around. But okay. Sometimes it disappears. So when there's something important to say, I'll try to move it more. Okay. Really fundamentally, the reason that resetting works, and this is what I want to show you right now, is that the inspection paradox and the resetting paradox that I just talked about are one and the same. They're flip sides of the same thing. So this is what I want to show you right now. How am I going to do this? So we're going to do some perturbative analysis. So I want to think about a process, and I'm going to take diffusion now. Again, as an example, I'm going to put a reflecting boundary here so as to regularize the mean. So now the mean doesn't diverge, and there's going to be a starting position and a target, and the particle is going to diffuse until it hits the target. And when it hits the target, I'm going to let it do this again and again and again and again. Like in my bus arrivals, I want to see this thing going on repeatedly. And now what I'm going to think about is some long observation time. And in this long observation time, I'm going to introduce a small resetting rate, infinitesimally small, such that the resetting rate times the observation time is much smaller than 1. So now what's the most likely thing that would happen if you have a very small resetting rate? The most likely thing that would happen is nothing. You're not going to see any resetting events in the observation time. Fine. So to 0 order, if you just introduce resetting, there is no effect on the process or on how fast the process completes. But what is the first order correction? So the first order correction can be determined by looking at the next likely thing that could happen. And the next likely thing is that you're going to have a single resetting event during the observation time. And I want to think about this single resetting event, and I want to see where does it occur along the observation time. So I'm going to take my observation time and I'm going to split it 3 ways. A1, this is going to be the first piece, B, and A2. And now I'm going to ask, what is the probability that resetting happens here in this interval B, given that just a single resetting event occurred in the entire observation time? This is basically the probability that I will have 0 events in A1, 1 event in B, 0 events in A2. And then I also need to divide by the probability of the event by which I'm conditioning, which is the probability to have a single resetting event in the entire observation time. How do I compute these probabilities? I just recall that what I have here is a Poisson process for the resetting. Resetting is done at a constant rate, hence it is a Poisson process. Hence, the number of resetting events in an observation time is going to follow the Poisson distribution. This is true for the entire observation time, but it's also true for A1, B, and A2, because these are disjoint segments. And so if I take the Poisson distribution and I just plug it in to the formula that I had before for the probability to have a single resetting event here in B, and I cancel all the things that I can cancel, what I discover is that the probability that resetting will happen here is just B over the observation time. This is uniform. This means that resetting falls uniformly along the observation time, because this partition that I made here is completely arbitrary. Okay, so resetting happens in a uniform distribution along the observation time, and this means that this is just like random inspection. So if I come at some random time, it's just like resetting with some very low rate. It's going to have the same statistics. And this allows us to use the insight that we gain from the inspection paradox to better understand resetting phenomena. So now if you imagine what is going on, I want to think about the same thing, a process that goes on, completes, and then it starts all over again. And I want to think about turning on a small resetting rate and resetting occurring at some random position along the observation time. And now I need to compare two situations. A situation where I arrived at this random point and I just let my process just go on until it completed its natural course. How much time, if I come at some random time, how much time will it take it to complete? This is just the residual time that we considered before. You come at some random point, how much time does it take the bus to arrive? It's the residual time that is the right random variable to consider. Then on the other hand, if resetting occurs, then what happens is you take this process, you stop it, and you start it anew. And if you start it anew, then you draw a new new completion time from the original distribution, and then this time is just t. So when in which cases will resetting expedite the completion of a process? When this guy t on average is smaller than the average of this guy, the mean of the residual. The mean of the residual is just that. It can be written in terms of the average of t, but then you also have this contribution coming from fluctuations. And it's convenient to take this inequality and rearrange it such that the CV is going to stand on one side. And what you see after you do that is that this inequality will hold if and only if CV is larger than 1. And so what you see is that exactly in these situations where coming to the bus station, you're going to wait a time longer than the mean time between bus arrivals, these are the situations in which the introduction of stochastic resetting will expedite the completion of a stochastic process. And this process doesn't need to be a diffusive process. It will, it's actually a general statement. Why does it happen? Fundamentally, it happens because what resetting is doing is taking a long completion time on average, the mean of T-res, and then replacing it with a shorter completion time. So you're trading long completion times with short completion times when fluctuations in the completion time are large. This is what you're doing, and this is fundamentally what allows resetting to expedite completion of stochastic processes. I want to explain how this feeds on a certain universality that occurs when considering optimal resetting or stochastic processes that are reset at an optimal rate. For this, I will go back again to the example of diffusion. And here I'm plotting the mean first passage time of a diffusive particle to a target, distant L apart, and I'm plotting it as a function of the resetting rate. And what you can appreciate is that when the resetting rate is very low, you go to the limit of no resetting, the mean first passage time becomes very large. We know that if you don't reset, the mean first passage time will diverge. If the resetting rate is very high, you're not really giving this particle a chance to explore its surroundings, and hence this mean first passage time will also become very large. But in between, there's a sweet spot. There's an optimal resetting rate. And if you reset at this rate, you minimize the mean first passage time. What is this optimal resetting rate? Well, we can understand it from physical considerations. You just want to wait for this particle to diffuse a distance L. And this happens in a time that is L squared by D. This is the diffusion time. And then if it hit the target, great. If not, maybe it's on the other side. And then instead of waiting it for to come back by diffusion, you want to bring it back by resetting. Okay, but this is just on the average. Some particles will take more time to arrive to the target, and some particles will take less than the mean that is plotted here. So another thing that we can do is look at fluctuations. We can look at the standard deviation over the mean first passage time with resetting, basically the CV of the first passage time with resetting, as a function of the resetting rate, now normalized by the optimal resetting rate. And you see that all these free curves then fall on top of a single master curve. And this single master curve at the optimal resetting rate is exactly 1. So you see that at the optimal resetting rate, the relative fluctuation, the standard deviation over the mean, is exactly unity. And our way of saying this is that the standard deviation in the first passage time is equal to the mean first passage time when you restart at an optimal rate. What's interesting is that this is not unique to diffusion. It's actually a property of any process that you restart at an optimal rate. That will basically bring you to a minimum of the mean first passage time. So how is this related to the result that we just saw? I already told you that if you have a process, what will happen if you want to determine if the mean first passage time of this process is going to go up or down when you introduce resetting, what you need to look at is the standard deviation in the absence of resetting. If this is larger than the mean, if the CV is larger than 1, then the slope of this thing is going to be negative. Introduction of resetting is going to take you down and expedite completion in the beginning for a small resetting rate. But now this turns out to also work for higher resetting rates. So if, for example, I reset a process at some rate R that is not necessarily small, what I can do is look at this entire process that is being reset at a rate R as a black box, a new process. And then I can ask, what will happen if I will reset this process at some small rate delta? The CV criteria tells us that if the standard deviation of the reset process is larger than the mean, then introducing another small resetting rate delta will take the mean further down. So basically, resetting, but now resetting a process at a rate, resetting a process that is already being restarted at a rate R with an additional rate delta is the same as taking the original process and restarting it at a rate R plus delta. And so what will happen is that this will continue to go on. This will continue to go on. The slope of this curve is going to be negative until it reaches a minimum. And at the point where it reaches a minimum, it will cut the standard deviation. Why? Because if it was the other way around, if the standard deviation would have been higher, then increasing the resetting rate some more would further lower the mean, which is in contradiction to this being an optimal point or a minimum. And if it was the other way around, maybe the standard deviation would have been smaller, then increasing the resetting rate would increase the mean. And this again is in contradiction to this being an optimal point where the derivative vanishes. And so optimal stochastic resetting renders fluctuations in first passage time completely universal. And this is again a result of the inspection paradox and the CV result that we just saw. Okay, so at this point, the point of optimality, the standard deviation of any process that restarted optimally is going to be equal to its mean. Now, before I conclude, I want to say something about resetting taking time. So up until this point, we consider resetting as something that happens instantaneously in zero time, but in fact, this can never happen. This can never happen in real systems. In any real system that you will consider, resetting will take some amount of time. And so perhaps what we want to be thinking of really is first passage with resetting, but then also with some time overheads. So when you reset, there's going to be some time overhead before you can start anew. And where is this particularly important? It's particularly important when thinking about enzymatic catalysis at the single molecule level, where this is exactly the scheme that you have, but to a change of labels. So this is how we describe enzymatic catalysis. An enzyme binds and unbinds a substrate to form an enzyme substrate complex. But then when they're bound, you can have by the process of catalysis a product formation. So the enzyme will either cleave a bond or add a bond or do something to the molecule, and it will change it from substrate to product. And these kinds of processes happen millions and billions of times in our bodies every day. This is in fact what's making our bodies tick. But here you see that catalysis is just some first passage process that needs to complete. Unbinding is de facto resetting this first passage process. And then before you can start again, you have to wait some time for a molecule to bind your enzyme, a substrate molecule to bind your enzyme. And so there's a natural question of how, in this system, when you have time overheads, how does unbinding affect the rate at which you accumulate product? And you can imagine that it could work both ways. There could be situations where unbinding will expedite product formation, expedite the completion of the catalytic process, and there's also the other option. So how do we determine which of the two happens? We just generalize what we did before. So what you can do is, again, look at cycles of binding, catalysis, product formation, binding, catalysis, product formation, and imagine what happens when you introduce a small unbinding or resetting rate. So you visit the system at some random time, which is here, and you capture it in the middle of a catalytic event. If you just wait for it to end its course, the time it will take it to complete is the residual time. If you reset, on the other hand, then you're going to have to wait a penalty that is coming from the binding time, and then another fresh catalytic step, which will take t units of time to complete. Again, t is a random variable. Now, when will resetting act to expedite completion or increase the rate of product formation? When the average of T on and T, the sum of these two guys, is smaller than the mean residual. And we have, again, a formula for the mean residual from the inspection paradox. So what we can do is rearrange this thing, and you will perhaps not be surprised that what we get is something akin to what we got before. When there's no penalty, when the binding time is 0, CV is larger than 1, this will tell us that resetting expedites the process, the catalytic process. But if you have a penalty, if you have some time overhead that you need to pay, fluctuations must be larger than 1, fluctuations in the sense of the CV, for resetting to actually help, such that you will trade long completion times, which ones that are shorter on average. And this is exactly the correction or the penalty that comes in twice the mean binding time over the mean catalysis time. So this is dimensionless. Another situation where resetting takes time is when considering diffusion with stochastic resetting. And this is the first experimental realization of this process. You take a particle, a colloidal particle, and you let it diffuse. And now from time to time, you come with optical tweezers and you take the particle and bring it back to its starting position. These experiments were done in the lab of Yael Weichmann. And I think that you can appreciate from the movie is that it takes time to bring the particle back to the origin. And moreover, bringing the particle from far away will take more time than bringing it from a place nearby. And these are all considerations that you have to take into account when you want to answer questions like, will resetting hinder or expedite the completion of a process, maybe the arrival of this particle to a certain barrier or threshold that I put right here. But again, the inspection paradox comes to the rescue, and we can perform the same type of analysis. The only difference is that now this time it takes to restart, it actually depends on the position of the particle at the moment of resetting, and this position is random. So there's going to be some maybe deterministic time given this position. If I tell you where you are, and maybe you're coming back at a constant velocity, then you know how much time it will take you to return. But this position itself is random. Nevertheless, if you average the mean return time, which is the penalty, and the mean completion time, this is what happens after you reset, and you again compare them to the residual, the mean of the residual, the time it will take you to complete without resetting, you get the condition that will determine when resetting will expedite the completion of the process, even in the presence of these spatiotemporal or these delays that have some spatiotemporal coupling. You can rearrange this and write it in a very simple way, akin to what we had before. For resetting to expedite completion, the CV squared needs to be larger than 1 plus a penalty that is just twice the mean return time over the mean completion time. Similar to what we had before, but maybe the catch or all the details lie in how you compute this average. And I'm not going to go into this right now unless somebody asks, then I can describe how or with respect to what density function do you need to compute this average of the return time. But it is an average return time. I want to say that you can combine the two results that we just got to consider or compare free range search with home range search, these two different strategies in which animals search for food. So you can think about a situation where you have a butterfly, and this butterfly flies around and it tries to find a flower, and it never stops. It only stops when it found one of these flowers in the arena. And in the contrary, you can think about a bee that roams around, but then, you know, if it finds the flower, that's great. If it doesn't, up until some time threshold, it will come back. It will take it some time to come back. This time depends on where it is. And then after it gets home, maybe it will spend some more time over there, and this cycle will repeat itself. And then you can ask, okay, which one is better? How should I search in order to find the flower faster? Should I do free range search without stopping, without resetting, without resting, or should I act like the bee? And it turns out that there is no unique answer to this, but we can tell when should you do this and when should you do that. And the answer is that search with home returns, basically searching like the bee, will provide an advantage. It will help you get to the flower faster under conditions of high uncertainty, again in the CV sense. So this is basically combining the two results that we had before, when CV is larger than 1 plus a penalty that comes from these idle times that you spend at home. These are the overheads. And then also the spatiotemporal overheads that come from the fact that you need to come back home. This, when fluctuations in the first passage without resetting, in the sense again of the CV, are larger than what you have here on the right-hand side, then it would be worth it to do search with home returns. Okay, I'm almost done, but there's one more thing. Sorry, there is one more thing that I want to share with you before I conclude my talk. So we've already discussed how resetting drastically affects the answer to this question: when will the particle reach the origin in a diffusive system and in other systems? But another fundamental question, really fundamental question that was asked in this paper, Diffusion with Stochastic Resetting, is where will the particle be if you wait some time in the presence of resetting? And the fact that you have resetting drastically affects the probability distribution to find this particle anywhere in space. And generically, it leads to a new kind of non-equilibrium steady state. So now the question is, can we understand this new kind of non-equilibrium steady state with the aid of the inspection paradox? And it turns out that yes, we can. And this is in many ways even easier to do than what I did so far in my talk, discussing first passage with resetting. So let's think about steady state with stochastic resetting. So we have some process, maybe diffusion, and we wait a long time. We impose resetting and we wait a long time. And then we want to see what is the steady state. What is the probability to find the particle at some position in time? After, we've let this, some position in space, after we've let this system evolve for a long time. So you can think about it as follows. You have here the first resetting event, and then the second, and these are the length of these intervals. And you can draw a parallel between this and the bus stop example that we saw in the beginning of the talk. So maybe, every time I reset is exactly when a bus comes to the station, and I have the first resetting interval, and then the second, and then the third, and so on and so forth. And if I want to understand the steady state, what I should be doing is let this system evolve for a long time and then come at some arbitrary time and inspect the system at some inspection time. And what I'm going to see is I'm going to see the system having evolved for a time t inspection from that passed from the previous resetting event. And if I'll know the statistics of this time, I'll be able to determine the steady state, because here everything started anew. If I just know the free propagation time, the statistics of this free propagation time, t inspect, I'll know everything. So you can convince yourselves, and this is very easy to do. You basically repeat the same calculation that we did before, that on average, this time is going to have the same mean, the mean of this time, and actually the entire distribution of this time is going to be the same as the residual time that we considered. Here we're looking back. Previously we were looking forward, but from symmetry it doesn't matter. And so the mean of this inspection time is going to be sensitive to fluctuations in the resetting time distribution. And in particular, it's going to be equal to the second moment over twice the first moment, or half the first moment times 1 plus CV squared, just like the mean residual waiting time. And so now if for simple diffusion, the MSD grows linearly with time and never reaches a steady state, so you have 2 dt. If you impose resetting, all you need to do is take this MSD and average it with respect to this inspection time. So you basically come at some time. This means that the system evolved for the inspection time. And if you take average with respect to this random quantity, you will see that this is the MSD with resetting. And again, it's not only sensitive to the mean of the resetting time distribution, it's actually, because of the inspection paradox, biased towards larger propagation intervals, and hence sensitive to fluctuations in the resetting time distribution. When this is large, you're actually going to have a mean square displacement that is much larger than what you initially expected. And in fact, you can generalize this beyond the MSD to get the full distribution, the full steady state distribution of a process which you reset stochastically in time. How do you do that? And this is really going to be my last slide. If you have some probability distribution describing your process without resetting, something that tells you what is the probability to find your particle at position X at time t, all you need to do in order to get the steady state distribution with stochastic resetting is take this probability distribution and average it with respect to the inspection time. Now, what is the density of this inspection time? Well, first, you need to observe that in order to inspect or in order to see an inspection time that is t, you have to fall in an interval that is at least has a length L that is at least t. And so the contributions to the density at point t are going to be coming from intervals that are t and larger. If you fell in such interval, the probability to see an inspection time t is just uniform on this interval. So 1 over L, the length of the interval. And then what is the probability to find such interval, to fall into such an interval? It's not just the density at which these intervals occur. It's multiplied by the length of the interval because of the inspection paradox. So longer intervals are more likely to be chosen because they're longer and you're giving equal probabilities to time points. And so the L and the L cancel out, and when you integrate, you just find that this is the probability that the resetting time is larger than t. This is not a density. But to get a density, it's very easy. You just normalize by whatever is the right normalization factor. And the right normalization factor here, if you integrate this from 0 to infinity, it's just the mean of the resetting time distribution. And so this gives you a formula that allows you to compute the steady state distribution of any process under stochastic resetting with the aid of the inspection paradox. All you do is integrate this propagator, the probability density without resetting, with this density, which is the density of the inspection time, the random inspection time. Okay, so with this, I would like to conclude. I didn't have any new results in my talk today. I just showed you that much of what we know, many of the results that were derived with much effort by us and others in the literature can be obtained almost directly with very little effort if you're just aware of the inspection paradox and are willing to use it. So the effect of resetting in many ways is a direct outcome of the inspection paradox, both in first passage problems and when you're considering non-equilibrium steady states that arise due to stochastic resetting. Again, a huge tribute to Dr. Arnaud Pal and Dr. Sarah Kostinsky, who wrote this paper together with me. And before I conclude, I just want to say we're celebrating 10 years anniversary of diffusion with stochastic resetting, a paper that really opened a field in statistical physics. I hope that you got some of the flavor from my talk today, and what I want to say more is that we're still open for submissions until April 30. This is pretty close, but probably we're also going to give 3 months extension to the submission deadline. So if you have something in preparation and you're thinking about where to submit it, and it's in related to stochastic resetting, please submit it to this special issue. And by no means I was trying to imply that so I showed you that we can gain a lot of insight by the inspection paradox, but still there are a lot of things that we can do maybe from this viewpoint. So we had 10 beautiful years of stochastic resetting, and I'm really actually looking forward to the next 10 years where we're going to learn some new things that we really don't know right now and answer some new and exciting open problems. And with this, I would like to thank you very much for your attention, thank the funding agencies, other members of my group, and take any questions if there are questions.
Okay, thank you, Shlomi. We're actually, we've run over time, so probably time for one or maybe two questions.
Thank you. I went a little too long.
I have just a question on the time overheads, just to clarify something. So
please, yes.
Right, you had a sort of tau x, which was the time to return, given that the position you reset to was x. And I just wanted to check that the resetting rate didn't depend on x.
So what tau of x is, thank you, Martin, for this clarification question. What tau of x is, this is the time it takes you to return to the original position from position x, which is your position at the resetting moment. Right. The resetting moment is random, hence this position is random, but these two things, they don't depend on it.
Right, that was just what I wanted. That was it. That's the point.
So the resetting rate is agnostic to what the process is doing. It comes from some external mechanism. Yes.
Thanks, Martin.
Yeah, but just to continue with that theme, there's been some works recently where the resetting sort of is not externally imposed.
Yeah. I know. So we're not done, and there are other questions to be explored. I think that this is. I agree. It's fascinating. There are situations where you're going to have the resetting rate is going to have some spatial dependence in it from some physical mechanism that does that. And there have been works on this. I think from I'll remember in a second, but it is a beautiful direction to consider with the good physical motivation.
Okay, I think we probably ought to stop there, but we can continue informally afterwards. But I'll stop the recording at this point. So thank you again, Shlomi, for a very nice talk.
Thank you very much. Thank you very much.